And welcome back. This is the extremely open science stream for what's the date today? May 27, 2025, and we will be picking up where we left off last week. I got my coffee, got my I think the stream is on. Let's see if everything's fine. Everything seems good. Right, so recap. Let's go. So last week was a little bit of this consolidation week. So we expand the frontiers of what the code does. Then we spend some time cleaning it up. Sometimes we spend some time deleting it, and that actually goes very fast. But when we like what we did, we spend some time cleaning it up, making sure it actually does what we expect it to do. Maybe making it faster if we want to scale it up, etc., etc. So what we did last time was doing exactly this type of cleanup, and I will share my screen. 1, 2, 3. There you go. All right. So what we did last time was this type of cleanup, and actually, off stream I did an even bigger type of cleanup, which was one of the purposes of this project is that we dog food our own tools. So we use our own tools, and when our tools have limitations, then we get frustrated with the tools as much as any other user would, and then we are incentivized to and able to fix them and fix them for everybody. Or in this case, wasn't even an error. The problem that was frustrating was that loading and unloading these Polars data frames was taking a long time, and when was doing it through Jug, and so Jug generally uses this general Python pickle module, and if you have a data frame, apparently that's very, very slow. And so off stream I actually improved Jug, and I showed this. So I improved Jug to special case saving this particular structure, and it went from about 30 seconds, this was what we were seeing in the Sardine project, down to effectively instantaneous. So this was what we were doing. So this is what we were doing before. Just here. Doesn't matter. Okay, so this loading these z-scores now, boom, there it is. It was taking, for some of them it was taking several minutes. Now this is like, boom, it's there. All right, so this is something I did. I did it off stream. I didn't show, but I showed it in the recap a little bit, and then what we need to do is to then, wrong file, is to then use Pixie. And now instead of using the version of Jug that was available from Conda, we are using a very specific, so this unreleased version of Jug. And again, I think it's very good for us as a project for Jug that I'm using, and I'm using this test version. So any problems with this test version, we will encounter it here. If after a few weeks of using this, it seems okay, we don't see any errors, it's significantly faster, then we will release it, and then everybody who uses Jug will benefit. Actually, to be honest, I've always been a bit disappointed that Jug did not catch on. I think it's a really great tool. It does seem to be a little bit of a, there's a learning curve, and that seems to take a while for people to, but the handful of people who have actually really used it seem to be very happy, and I myself keep using it all the time. So but I will keep using it. I basically cannot do any work without it, and so maybe you want to try it out as well. And if you do try it out and run into troubles, do let me know. We have also a mailing list with, again, not many people, but maybe 50 whatever users that have signed up for the mailing list. So anyway, so that's where we left off. We had spent some time trying to reproduce this figure. So let's just, for example, so now if we do this figure, this would used to take multiple minutes, and now you can see it goes. It takes a few seconds per, less than a second per sample or per genome. There you go, one. Right. And what I wanted to now check, okay. So now that we can do this much faster, we can maybe finally do what we wanted to do last week, which is, can we get slightly different representations of this? So in particular, some way I want the representation where we rotate, where we are going to be rotating. So instead of taking, so here we have the mutations on the x-axis, and then this ESG score, excess of small gene score, on the y-axis. I kind of want to rotate that a little bit, and then so get the, what would be, so if we set the threshold, so there's two things, so let's think about it this way. If we set a threshold on the excess of small gene scores, we make two types of mistakes. One is we fail to catch some genomes that are bad, and the other mistake is we mistakenly classified some genomes as bad, even though they're good. See, right? This took a few seconds. This took like a minute or two, whereas before it would take a good half an hour. Right. So for example, here, let's say if we set the threshold at -700, it would be excellent because we would have no mistakes of the kind, no false positives, but we would have a lot of false negatives, or some of these genomes, even with 5,000 mutations, would still not catch them. But let's do that. So what we okay. So let's do that. So we get, okay. Okay, that's not great. Okay, sorry. Oh, sorry, this is all, sorry about that. So this is already, yes, this is already. So let's do this. So let's say threshold. I'm just going to start typing code. Threshold equals -700. False positive equals what does this do? No. I think it's I think something like this. And then if the threshold selects the minus, let's say 100, okay, I think this is what we want. So the minimum number of mutations such that for that such that for that right, so let's do this. So let's okay, so anything with a 0, it's a false positive, right? So let's do, okay. Let's just, okay, this is not bad. Let's do it. Yeah, this is actually not bad. So I want, yeah, right. So this is what, yeah. Okay, this works. This works because, so right now, so sorry. Oh, this is nice. reverse this. Right, so this is what we get. So this is a actually, yeah, I don't like this. I think it should be like this. Yeah, right, okay. So it should be something like this. So as we increase the score, we get the rate of false positives drops. It drops quite precipitously, very fast, and then eventually drops to 0, but then we are a bit too strict and we miss some things. First of all, I actually do like this. I do like this visualization, so I am going to put it here. I don't want to call it data, I want to call it precision recall. Oops, yeah, so not really precision recall. I should have done a precision recall curve, damn it. Oops, sorry, yeah, let's do a proper precision recall curve. No, is this a precision recall curve? Similar-ish. It's close enough. So let's do precision. Actually, I wanted to do a rock curve. So rock curve, yeah. It's the best use of my time right now. It's not. It's a little bit different from. Yeah, let's keep this one instead. Yeah, let's keep this one instead. All right, so we have this one. So this is a good summary of the statistic. So the problem is right there, it crosses. And then, and what's nice about this is now, first let's actually, okay, let's, no, I don't want that, yes. So I'm going to lower the sound just a tiny bit so So move the all right, there you go. Okay, now what's nice about this is now for example, what would the curve be if I just change? What does this look like if I do this? And whereas before it would take an hour to try something new, now it's going to take a few minutes. And so we can play around a little bit more. But maybe what we should actually do is look at these. There's two organisms there. What are they? What's going on? So I think there's two ideas that we thought about exploring. So one would be, instead of using all OGs, just focus on ones that are more stable. The second idea would be, instead of using all directly, maybe we, if it turns out that these guys here, these genomes there, have shorter genes overall. It's not concentrated in a few. Maybe we can adjust for that. So that would be the other idea. So what do I want to do? Okay, so that's going to finish now in a few. There it is. Okay, that was kind of a terrible idea. Oh, that was a terrible idea because maybe I just need to add a 0 here. Oh, right, sorry. Sure that, to be honest, I'm not sure it changed that much. Like if I compare these two, so this is the previous one, and this is just fiddling and changing the threshold. This one, obviously the numbers have changed, -500, but it's stretched out a bit more. I'm not even sure it matters that much. So I am going to go back to this. I just skip that one. And let's ask the question. So what's this genome? What are these 2 or 3? Okay, we can close this. We don't need it. We don't need this. We don't need this. Okay. Yes, wait longer. So if we could just get rid of these, or figure out how to identify them, and then correct that such that we don't call them as false positives, then I think we would be done. Actually, then this would be it. This would be the metric. Let's just see. By the way, let me just check. This whole thing takes. Okay. Doesn't matter. Okay, so this is the let's pick this organism here. Right, so we pick this organism. Let's just see this. Are all of them? I'm gonna close this. Does it exist? Oh yeah, sorry. Sorry, a bit of pandas thinking right there. Keeps trying to. Oh, I see. Oh, god damn. This is annoying. How do you do this? This. Okay, right, so some good news, bad news, I guess. So if I look at the, so these are the ones, these are the outliers. And if I look at the median z-score, they already show up as outliers, so that's what's this organism, by the way? Oh, mycoplasma. Okay. Okay. All right. And what's the other one? 1948890. Okay, that one I don't know. Mycoplasma. I mean, that makes some sense because things that are right. It's mycoplasma, intracellular. These things tend to just be weird. Okay, but sure what I'm, yeah. I think this is what we, this is actually good. So what this means is that so if I look at the median z-score, or z-score, and so if it's below, still, I don't like how, so here, these ones are still, maybe I should do it the other way around. No. So this is the median z-score. If it's below this value, minus 0.2, then I mean, the logic only works if this is, yeah, the problem is that let's do, okay. Yeah, this doesn't work. Right, sorry, this doesn't work because we don't know if we have this genome. We see could be very messed up, or it could be. Okay, this logic doesn't work because this. Yeah, but if you have this genome here with 4,000 mutations, oh, that one is one of the bad ones, but that one. Yeah, right, this is it. Yeah, this one's good. It's gonna have yeah, this one's good. Has a z-score ESGS of 0 for no mutations. But when you add mutations, it ends up with a lot of. All right, so this idea does not work. So the other idea is to find orthologous groups that are very, very stable. I mean, having said that, the results we got before were not bad. I'm not unhappy. I think we have something there, and if it has a 2 or 3% error rate, it might still be worthwhile pursuing. because we might still be able to claim, that there's something there. And then if it doesn't work for Mycobacterium tuberculosis, or that was the other one, that was the cow one. Was what? Yeah, if it doesn't work for some few weird bugs, that's also interesting. We can say, okay, this metric will fail for certain. But it would. All right, let's go back here. All right, let's still sort of yeah. Maximilian. Okay. Okay, the medians is not a good. Let's just run everything again. This loads everything. So let me. So these are the plots we have generated. I'm looking for 28903. Where was it? Maybe I didn't generate it. 1948. Oh, there it is. 28903. Yeah, so this is the compared to, I don't know, let's take a So this is the 28903. So this is how the so I'm going over. So this is 28903. So this is the Mycobacterium. You can see the whole curve is shifted. But alas, in this one, 708248, with 1,000 mutations, also the whole curve is shifted. Okay, so just looking at the shape of the curves is not going to help us, because if we have the green curve there and the orange curve there, they look similar enough to me that I would be hard pressed to. Oh yeah, sorry, this was the... Yeah, some of... Okay, I'm not sure. The other thing that maybe some of these genomes have is very, very high coding density. So we have not looked at coding density at all, but that would be the other thing that we could look at, coding density. So let's not do that today. Okay. No, that we don't want. Yeah, let's just leave this here. top 5. And so really, it really, you know, drops very. So if I do this, it really drops really fast, right? So there's a couple of outliers there, and then boom, start. So if we could just identify this top few here, that would be great. We just identify these 4, even just these 3, then everything works. So because then we have a metric that we can use to. So what's special about these? Okay, let's wrap up. I'm just gonna put this here, wrapping up. Stream notes. But no, I actually don't want to. It's a little bit of work in progress, but just print out. Okay, now that I look at it, it's a bit stupid. Because we don't need to filter, because we're doing the top 5, so our pre and post filter is the same, and so it doesn't change much. It's just .93. I just want to be sure that it actually does run, and then we wrap up. Let's see, let me just quickly see, and then we wrap up. Yeah. Yep, okay. It just runs what I expected to run. Everything there. All right, we are gonna push that to get. So, you know, everything is always on Git. Always on Git, everything's there. Oops, sorry. I will actually push it now. Everything's on Git now, so check it out there. There's also a mailing list. I'll be posting a little bit there. I think this today was very, very good. We made a lot of progress. I'm pretty happy that that some variation of this I mean, I think the results we have so far would already make maybe a useful tool out of this. But if you can polish it just a tiny bit more, get it a little bit, maybe the other thing I'll try to do is just try a little bit more. So we've been using these 200 genomes as a test. Maybe let's just do 400. Let's just double it. That would also be great, just to have more data, see if we can identify these outliers, and then start writing up or wrapping up. But in the meanwhile, for today we are done, and I will see everyone here same time next week. Talk to you.